Have you ever really thought about how the medicines we all rely on are actually built, molecule by molecule? Well, today we're going to pry open the chemist's toolbox and take a look at the hidden architecture inside our pharmaceuticals. And it turns out a whole lot of it relies on one single, incredibly important connection.
Yeah, it really comes down to this one surprisingly common connection. It's an invisible chemical bond that literally forms the backbone of everything from antibiotics to life-saving antivirals. So, what is this molecular superstar?
Well, the hero of our story is something called the amide bond. You might not have heard of it, but it is without a doubt one of the most important chemical links in the entire pharmaceutical industry, and for a very, very good reason.
So, to put it simply, an amide bond is basically like a chemical handshake. It happens between two different kinds of molecules. One is called a carboxylic acid, and the other is an amine. And when they join up, they form this super strong, really stable structure that is just absolutely essential for so many drugs to do their job.
Just how essential is it? Well, get this. According to industry research, the process of making this one specific type of bond, just this one, accounts for a staggering 16% of all reactions that happen in pharmaceutical chemistry labs. I mean, think about that for a second. One single connection makes up a huge chunk of all drug discovery and manufacturing. That's wild. But here's the twist. For a reaction that's so incredibly important, making it actually happen is surprisingly difficult. You could say there's a fundamental matchmaking problem that chemists have been wrestling with for over a century.
You see, if you just take the two partners, the acid and the amine, and mix them together, you'd think they'd form that crucial amide bond, right? Nope. Instead, they just neutralize each other and form a stable but completely useless salt. It's like they like each other, but not in the right way to actually build a medicine.
So, this means chemists need a clever workaround. They can't just mix and stir. They have to do something called acid activation. Basically, they have to give the acid a little chemical energy boost so it gets ready and willing to form the right kind of bond with the amine. And to do that, well, they need some special tools.
And this brings us right to the chemist's toolbox. It's filled with all these specific chemicals called coupling reagents, and each one is designed to help make that perfect molecular handshake happen. Let's pop it open and take a look at a few of the most important ones. Okay, first up, you've got the classics. Think of reagents like thionyl chloride as the heavy-duty hammers in the toolbox. They're powerful, they've been around forever, and they just get the job done. They work by turning the acid into a super reactive form called an acid chloride.
Next, we've got the workhorses. These are the carbodiamides. The one you see here, EDC, is kind of like the industry's favorite power drill. It's super versatile, it's reliable, and it's just incredibly popular for a huge range of different jobs.
And then you have the precision instruments. A reagent like T3P is more like a chemical scalpel. You use this when the molecules are incredibly complex or delicate, and you absolutely have to avoid any unwanted side reactions that could mess up the final drug. Here, it is all about control.
So with all these tools sitting there in the toolbox, how on earth do chemists decide which one to use? Especially when they're not just making a tiny bit in a lab, but scaling up to hundreds of kilograms for a medicine people need. Well, that choice is way more complex than you might think.
This chart here shows us the most popular tools ranked by how often they're actually used in large-scale production. And you can see EDT is a clear favorite. But look at thionyl chloride, that's SOCl2, right there near the top. Why is such a simple, old-school chemical still a blockbuster? It all comes down to a really critical balancing act. See, when you move from a lab bench to a giant industrial reactor, it's not just about what works best on paper. You have to weigh everything. How much does the reagent cost? Is it safe for the people working with it? What kind of nasty waste does it create? And, of course, does it actually produce a pure, effective drug at the end of the day? This slide right here illustrates those tough choices perfectly. Let's just compare two of those classic hammers. Thionyl chloride is incredibly cheap, which is a huge pro for any company. But it can form a byproduct that's known to be carcinogenic. Not good. Okay, so what about oxalic chloride? It's cleaner, its byproducts are just gases. The catch? One of those gases is toxic carbon monoxide. As you can see, there is no easy, perfect answer here.
This is summed up perfectly by the authors of the paper we're looking at. The search for the ideal reagent is the ultimate goal. But in the real world, finding something that checks every single one of these boxes, well, it's pretty much impossible. Every single choice is a compromise.
So let's take all this theory and ground it in a real-world example.
How do these tools and all these trade-offs actually play out when you're making a medicine that people depend on every day?
Let's look at this case study, creating a crucial HIV protease inhibitor. The chemists at Abbott Labs were facing this exact puzzle. They needed to form an amide bond, and they needed to do it on an industrial scale. So after weighing all the factors, the costs, the safety, the waste, they ended up choosing one of the oldest tools in the box, thionyl chloride. For that one specific critical step, it was simply the right tool for the job.
But what does this activation really look like down at the molecular level? Let's peek under the hood for a second, using a popular reagent called CDI as our example. Think of it as a chemical matchmaker. First, it temporarily links up with the acid. Then, in this clever little chemical shuffle, it breaks off, releasing harmless carbon dioxide gas. And that final step leaves behind a highly energized acid perfectly primed and ready to form that all-important bond with its partner. Pretty neat, right?
So what's the big takeaway from all this? Well, it's that creating the molecules of modern medicine is so much more than just clever chemistry in a lab. It's a really complex puzzle. Every single amide bond in a drug you might take represents a whole series of careful decisions, balancing the ideal reaction with the very real pressures of safety, cost, and the environment.
It's this whole hidden world of incredible chemical engineering. So the next time you see a prescription bottle, maybe you'll think about that invisible bond holding it all together, and the intricate, high-stakes puzzle that chemists had to solve just to get it to you. Pretty amazing when you think about it.